So where we left off was that prisoner's dilemma problem. We noticed that, oh man, the two prisoners, they should both confess, even though, like, if they could coordinate, they would both walk away for free without going to jail at all. But sadly, that's not what's going to happen because they can't trust each other. So they're both going to gravitate towards this equilibrium, this Nash equilibrium, named after John Nash. So we learned about that. I just have a few more examples of games, and games in quotes, because obviously these things are not like a board game, like all these prisoners talking to each other. That's not an actual game that you play in real life, is it? So let's talk about another game that is called cake cutting. So maybe you've played this with a sibling before. It's like you cut a cake, right? Like it's your birthday or it's somebody's birthday, or you just get a cake one day, and you need to share it. Like your parents are requiring you to share that slice of cake with your sibling. And the name of this game is that one person cuts the cake and then the other person chooses which piece they want. Have we played that game before? No. Like, that's supposed to be fair, right? If you cut it badly, then the other person's going to choose the bigger piece. So it's in your best interest to cut it halfway, right? So that's kind of the game. And like the internet is a little bit confused about whether this is a cooperative game or a non-cooperative game. Remember that a cooperative game, as far as game theory is concerned, is when you have an alliance, it's a good thing. Alliances equals a good thing. Though, in this example, it may be the case that you're kind of just forced to cooperate in order to get a good amount of cake. So, could be cooperative, could be non-cooperative. The internet is confused, and then therefore so am I. But yeah, the game is like one person cuts the cake, and then the other person chooses which piece of the cake they want. So, here's a cake, and here's an example cutting of it. If you're the one cutting the cake and you actually want cake, you should never cut it like this, right? Because your sibling, the other person who gets to choose, is going to choose the bigger half, right? The bigger piece, which is more than half. So what you should do then, the optimal strategy for you, if you actually want as much cake as possible, is to cut the cake exactly in half, right? Because then the person who picks, there's no difference between the two pieces. So then you're evenly sharing it at that point, whereas otherwise, like, you would be getting less cake because the other person gets to choose and they're probably going to pick the bigger piece. So that's probably the optimal strategy for this cake cutting game. And let's zoom into that. There's an idea here. There's a definition of optimality in game theory, and let's talk about it. So what we have done is we have allocated resources, essentially. We've allocated food, but this could be played at a larger scale with like economics and like money. But cake cutting is technically a resource allocation, and we call that resource allocation Pareto optimal. This is again named after somebody. This is another term in game theory. A resource allocation, we say, is Pareto optimal if, were you to change that allocation, somebody is worse off. So if you were to change the allocation in some way, like somebody gets a little bit more cake, then that always leaves somebody worse off. So it's a very utilitarian concept. What are then the Pareto optimal allocations for cake cutting? What are all the ways that we can cut a cake where if we were to change the way we cut it, somebody's worse off? Let's think about this. Is this Pareto optimal, like cutting it straight in half? According to the definition, I think so, right? Here's, we're cutting it straight in half, perfectly in half. Well, let's try to change it. If I change that cake cutting, if it was in half and now it's not anymore, like I cut a little bit more this way this time, and so we're going to get it like this. If that's my allocation instead now, it's not three-dimensional enough, let's say. There's the middle of the cake, right? If I cut it like this instead, now it's this piece, right, versus this piece. So is somebody worse off? I think so. Yeah, you probably, because the other person's going to pick the bigger piece now. So that is technically a Pareto optimal allocation, cutting the cake in half. And so that's nice. We have a word that we can associate with that perfect optimal cake cutting. But actually, no matter how you cut the cake, it's Pareto optimal. And so there's a little bit more going on here than meets the eye. But this is a useful term, I promise. Any cake cutting, surprisingly, is Pareto optimal. Like even this bad one, because if you cut it differently, right, if you cut it more like this instead, then you've made this piece that your sibling's going to take smaller, and so they're worse off technically. That's kind of cool. So every cake cutting is Pareto optimal, and though there is one that we kind of want though here. Okay, so Pareto optimality goes hand in hand with a Nash equilibrium a lot of the times, or you can think about both at the same time. And this term actually explains why this problem with the prisoner's dilemma was so confusing, why it was so counterintuitive. It's because this is the Nash equilibrium, like they're both going to confess, but it's a non-Pareto optimal outcome. You see that there's a better resource allocation that would leave people better off. So that's interesting. That helps explain it. So you can think about both at once, and so that's why I'm teaching you both terms. So that's Pareto optimality in a nutshell. And I think I have one last real term to teach you. Let's say that you're going to share an Uber or a Lyft with somebody, like you're going home from something, and you don't have a car yourself. So you're going to share a taxi with somebody, and let's see how much you should pay. What's the right way to share the bill? Okay, so this is going to be a cooperative game because two people are going to cooperate on the taxi and pay for it. And here's the setup. All right, here's why you would want to share a taxi with somebody. It's because somebody else lives on the way. Okay, so let's say that we got two people, person A, person B. We call them Alice and Bob in computer science a lot. So Alice and Bob, let's say that they share a taxi, and here's my best drawing of a taxi. Whee! Where's the front of the car? Let's say that this is the front of the car. And Bob lives way down here, but Alice lives over here. So Alice has a shorter ride, but it's on the way to Bob's house. Okay, so if Alice went and got a taxi by herself, she would only have to pay $5 because it's a shorter trip. Okay, but if Bob got a taxi by himself, that's a longer trip, right? He paid $12, and the price for both of them sharing the taxi is still $12, right? Because you're still going to Bob's house. Like Alice can run out real quick. That's fine. So there's no change in price for both of them to share the taxi, and it should be a little bit cheaper, right? That way. So the question now is, how much should Alice pay to fairly split the bill with Bob? Because if they were both to take this $12 and split it, right, $6 and $6, that's absolutely not fair for Alice, right? Because she would have, she's better off just getting a taxi by herself. So this is an interesting problem that's worth solving, and I'll show you one way to do it. This is not fair. Not fair for Alice. What's the best way? What is the number that we should calculate for Alice? She should be paying a little bit less than $5 probably, right? And Bob should be still paying less than $12. So what's something that's fair for both of them, right? How should they split the bill? And the way that you can find the right number, a decent number, is to use what's called the Shapley value to determine this number called the Shapley value for this problem, okay? And so the way that you do that is you think about all the jumblings of orders. So permutation just means orders. So it's orders of what? Orders of who pays the remaining bill, which is a very weird thing to think about, but I'll explain it with a drawing. And then you average them together, just like we were doing an average for the prisoner's dilemma. So here's how you can fairly split this bill. So what are the possible orderings of who pays what? So you can either have Alice pay the bill first, and then Bob pays the rest. Right? Alice pays her share, then Bob pays the rest. Or Bob pays his share, and Alice pays the rest of that. All right, and we're just going with the original prices. That's the trick. Okay, so if Alice were to pay first, then she would pay her full $5 in that case. She's paying her share, and then Bob pays the rest. It's $12 total, so Bob would pay $7 in that case. That's that universe. But if you do it like this, if Bob pays his share first, Bob will pay $12, right? And then Alice pays the rest of the bill, which is 0 at that point. So this is now the number that we're going to calculate. All right, we're going to take an average over how much each of these people should pay, and it's symmetric. So what we want to do is we want to determine what's Alice's cost in each of these situations. Alice pays $5 in this case, and Alice pays $0 in this case. And these are the two possible orderings of who pays what in what order, like the remaining bill. And what we should do then, like what the Shapley value tells us, the optimal outcome, or the fairest way to do this, splitting of the bill, is to take the average over all of those possible cases. So if you take the average, then that's the average of 5 and 0, that's $2.50. And apparently, according to math, that is like the optimal way to split the bill. So Alice is paying less, Bob is paying less, and it's much, much better for each of them than $6 split. Okay, so that's called the Shapley value. And think about that whenever you're getting an Uber with somebody one day. Any questions about that? It's an interesting number to calculate it. So averages, I guess, they come up a lot in game theory. All right, the last thing that I want to talk about for these set of slides before we switch to some different ones are an actual game. Let's talk about tic-tac-toe because it's a simple game. All right, I want to teach you an algorithm to determine the right way to play a tic-tac-toe game. Like if you were able to program this idea that I'm about to teach you, you would always either win or tie in tic-tac-toe. Okay, so here's how you do it. It's called Minimax, which is a cute name, and that's the way to win tic-tac-toe. Okay, so Minimax is a way of searching for the best possible move right now, given the game board, whatever it looks like. It's going to find the optimal strategy to play a game where different people take turns, and you're trying to win. Okay, so it's a game. It's an actual game for once, and let's say that this is our game right now, and we're X. It's our turn to go. X goes first in this example, tic-tac-toe, I guess. And so we want to determine, like, should I go here, here, or here? I think you can see where you should be going, but let's find a way to algorithmically determine this. Okay, so how can you find the best move no matter what your game board looks like? The answer is, for tic-tac-toe at least, is to just simulate the rest of the entire game. Okay, you got 3 options for X. Well, all right. Well, try it. Try X going there, try X going there, try X going the other spot and the third spot. You got 3 new game boards, right? And then try O's turn. O gets two options in each case, right? And just like keep on going down, down, down until you're done or somebody wins. And just like you can enumerate every single possibility of tic-tac-toe because it's such a small game. What are all the different game boards? It's like you got 2 options per 9 squares, right? So it's like 2 to the 9th power, which is not too many. It's less than like 10,000. Okay, so you can simulate an entire game even from nothing, which is exciting. Okay, so what we're going to do is use the Minimax algorithm to determine the best move for X. Okay, and what Minimax means is it's a combination of minimum, mini, and maximum. Okay, so we're gonna have some numbers that correspond to how good our board looks right now, or how good a move is. Okay, so when it's our turn, we're going to want to make the move that maximizes our chance of winning, which makes sense, right? We can assign a number to like a high number to mean we won, essentially. And so we want to make the move that maximizes our chance of winning when it's our turn. But also when we're simulating, we have to simulate O's turn as well because they're going after us. We're always switching places, right? So when it's our opponent's turn in Minimax, the nice way to do this and the way that's going to make it work is that we're going to assume that they're really good at the game and they're going to try to minimize our chance of winning at the same time as we're trying to maximize our chance of winning. Okay, so just assuming that they're really good at the game and that they're going to make the best move possible. And the goal is to, in spite of that, find the best move for us that's going to guarantee success or the best possible outcome. Okay, so that's the secret, and let me teach it to you. All right, we don't have a full house today, so let's just do this example together. I think would be the best thing. So I'd like, maybe I'll give you like a minute head start if you'd like to try. But here is that game state. I'd like you to try that example, right? Try to, like, let's make a chart of all the different ways that the game could be played from right here and say that it's X's turn right now. So for example, there should be 3 possibilities, right, for X. So X could have gone here, here, or here, and like that's the next stage of the game, right? So what would the game board look like if X went here, let's say? It would be X, O, O, X, right? The O still there, and then XX. And then there would be 2 others, right? And then you'd want to play the game for O after that. O has 2 spots to go to, and so like try those both out. And then like there's more down further, right? Because X needs to go one more time as well. So think about that for a second, and then I'll fill it in, okay? But that's the idea. Like maybe sometimes you'd have a million options, like 9 options if the board is empty. And you just enumerate all of them inside of a computer. and then you're going to do the minimax algorithm. And I still need to teach you the minimax algorithm, but we just need to first enumerate every possible way to play the game. Let's see here. So yeah, think about what it's going to look like, and then I'll draw it in like 30 seconds. That's an interesting concept, I think. This works for other games too. All right, so starting from there, let's draw it. Let's draw all the possibilities, and you want to stop once somebody's won the game. There's no like the board is over by that point, so you don't go any further if somebody wins the game. But starting with that, XOO and then O in the middle. So starting with this state, XOO, O in the middle, and then two X's on the right there. Starting from here. And it's X's turn. What are our possibilities? I'm going to try to give myself a lot of room here. So, I could do that, or that. And let's see, if I were smart, I would be able to copy and paste this. Let's see if I can do that. Otherwise, it would be a lot of writing. Copy, paste. Ooh, can I do it? But then I want to kind of make it smaller because I need a lot to put here. Ooh, I can even make it smaller. Nice. Nice. I like this. The power of technology. All right, so those are my three new copies of the board, and then X could have gone either here, right, there, or there, and that was X's turn. Those are the possibilities for X's turn, and then underneath that, it's O's turn now. Okay, so let's see. So O's got two options right here now. Either O could go here or here, right? So I guess it's probably faster for me to just draw it myself. But this is what you got to do in order to run minimax first. Okay? So, XOO, XO, XX, XOO, XO, XX. And then O could have gone either here or here. Okay? And then we're going to do the same one for this one. Now it's still O's turn. They have two options to go to again. Oh, sorry, excuse me. You can't move. This game is over, isn't it? X is won. Sorry about that. So, like, you stop when somebody's won. So who's won so far? This game is over. This game is not yet over, right? But this game is also over. So I have to go down further for this one. But this one's done. This one's done. And now let's try this one. So again, I've got two options for O to take. O could go one of two places, right? Let's see, we've got X, O, O, X, X, X. O could either go here or here, right? And if they go that second one again, it's kind of symmetric to the left side. They're also going to win, okay? So, let's see here. I still need to play the game to completion. I think it's just going to be, oh no, somebody's going to win for this case. So, all right, it's X's turn, and this is the board, right? O is moved. So there's only one last spot for X to go to, and X will win, won't they? So good job, X, if you stick it out until here. Oops. Sorry, it's so small. So there, if you go there, X would go there, or, and then this one as well, right? You only got one option, and it's X's turn. So they're going to fill in that one square. X. They're going to go right there, and they're going to win the game. All right, so it looks like most of your options are X winning. You got two options, though, where O wins. Okay, so that's the ways that the game could play out from right here. And that's what you start with, all right? And now what we're going to do, here's how minimax works. We're going to assign numbers to the winning games. Okay, so we start at the bottom, essentially, like the lowest level. Like when the game is over, you kind of figure out who won, all right? So X, let's say that from here, like we're trying to determine the best way to go, and so we're X. It's from the perspective of X, and X wants to win the game. So every time, every possibility where X wins, let's assign a positive number to that. Let's say positive 1 means we like that, X1. Okay, so positive 1 for that one, positive 1 for this one, positive 1 for that one, and every time O1, we don't like that if we're playing this simulation from the perspective of X. So we're going to say negative number for every time O1. So we're going to say negative 1 here. Negative 1 here. So that's all the endpoints. And then you kind of look up the hierarchy. Okay, so the secret is, what number do you assign to this? Okay, what number do you assign to this one? Well, it's going to be, this is, again, it's X's turn for this game, right? It's O's turn here, and now it's X's turn again. So we're playing this simulation right here from the perspective of X, and so we want to maximize our chances of winning. So over all the possibilities, if it's X's turn, they're going to try to, we want to maximize our chances of winning, so we're going to take the biggest number. And it looks like it's going to be positive 1. That's the only number as well. Okay, so the number associated with this is like, it's still a winning possibility for us. So we're going to assign that positive 1, and then we work our way up again. So now it's O's turn. Okay, from this game perspective, for this spot, it's O's turn, and this is where Minimax comes in. It keeps on flipping. So O wants to win the game, right? We're going to try to pretend that O is a good player of tic-tac-toe, and they're going to take the possibility that's going to minimize our chance of winning. So if O gets to play and they see these two options, which one are they going to pick? They're going to pick the negative one, right? The one where they win. And so we want to minimize over all the options when it's O's turn, when it's our opponent's turn, right? So the game board that we put here, we're going to assign this a negative 1 number to try to mean that we should avoid this situation, because even though we might eventually win if O messes up, we're going to assume that they're a good player and they're trying to maximize their own chances, right? So minimize ours. I hope that makes sense. And so this is kind of how the game plays out. It's like, all right, this is X's turn. We want to maximize over all the possibilities. There's only one thing, so the max of 1 is 1. And then this is O's turn again. They want to maximize their own outcome and minimize ours. So the options, they're going to take the minimum option for us. And so that means we can assign negative 1 to this, because O will totally make this move. We're going to assume that they're really good at the game. Okay, so that's the secret. And now we've assigned numbers to everyone but the initial game board. Okay, and this is again from X's perspective. Okay, this is from X's perspective, and so we would like to maximize our own chances out of all these options. So we're going to take the maximum over all of them, and that's going to be the positive 1. So that's this one. We can assign positive 1 to this outcome. And that means, what that finally means is, we better make this move as X. Does that make sense? That's what Minimax tells you. It tells you, all right, you would like to make the choice that's going to maximize your own chances of winning under the assumption that O is really good at the game. So you don't want to go down here, even though you could possibly win down that way. You don't want to go down that way because O is probably going to win and beat you. Okay, this is the one way that guarantees success. Okay, and so that's the secret. Does that make sense? That's Minimax. You can program that with enough thought, and that is a way to win the game no matter what, or at least tie. Okay, so that's how it's going to work, and you can do this from the initial game board, and you'll figure out the best move is probably, I think it's start in the middle or something if you're X, something like that, guarantees the best outcome for you. But that's that. All right, I hope that makes enough sense. And so that's finally an example of actual game theory in a game. This is also technically an artificial intelligence kind of algorithm, but yeah, you might see more about it if you learn more computer science. Yeah, I think that's what I wanted to talk about for game theory. And the last thing that I want to do today, in the next half, I think we only have time for a topic called recursion. All right, so it's a fun one. It's going to melt your brain a little bit, but I am very excited to teach it. It's a fun topic to teach, for sure. All right, so let's talk about recursion. It's a word. Have we heard that word before, recursion? It's just, it doesn't really come up too much outside of computer science and mathematics, but it's so interesting, all right? You've seen the ideas, I think, but what recursion is all about, the slogan is, we want to solve a problem in terms of that same problem, which sounds very circular. We want to find the problem inside of itself the way to get out of the circularity is to find a smaller version, okay? So like that's what you might be guessing or thinking about right now. There are a ton of memes about recursion on the internet because everybody like they hate learning it. It's a harder topic, but it's still very fun once you get it. Okay, so isn't it circular reasoning to solve a problem in terms of itself? Like, are you never sounds like you're never actually going to get to an answer. The secret is that with recursion, you're not going to find the problem, the same version of the problem inside of itself. You're going to find a smaller version of the problem. All right. So a good graphical example of kind of how recursion is going to work are these Russian stacking dolls. So like you got the outermost one, which is like the original problem you want to solve. And then inside of that, you find a similar thing. You find the same problem. You find another doll, but it's smaller. Okay. And the goal is like there might be a smaller problem inside of that one, inside of that one, inside of that one. But eventually it gets so small that it's immediately solvable. Like there's a last one. There's a smallest one. Okay. So that's what we're going to look for today. And so, yeah, plenty of memes about that. It's like infinite zooming. That's what recursion is all about. And then the only way to solve this game, if we've heard of it, it's called the Tower of Hanoi problem. Like you got to move the pegs from here to here, and you can only put smaller ones on top of bigger ones. Recursion will tell you how to play this game in the optimal way, which is exciting. Okay, so yeah, let me teach you recursion. So it's not circular reasoning as long as the problem gets smaller. All right, as long as the problem gets smaller, everything's fine. So like you got your original problem. What you want to look for is a smaller version of that problem inside of itself. So here it is. Find it. Try to solve it, and then you can use that answer to solve the original problem. All right, that's going to be what recursion is all about. It's going to look very similar. All right, you're going to use that smaller problem's answer to solve the bigger problem. All right, so yeah, what recursion really is, the correct definition is you want to solve a problem in terms of smaller versions of itself. And this probably still sounds very vague and confusing. I have a good example in just a second, okay? I promise. Let me say some words first, though. But yeah, what you do is you find a problem that you can find a smaller version of it inside of itself, and that smaller version is called the sub-problem. And then you go and you find that answer. You get to assume that you get it, which is weird to think about, I know. And then you're going to use that answer to solve the original problem, okay? That's going to be how that works. So the quintessential recursion example, the one that everybody likes to teach first, is factorial. All right, so let's just do this together. Finding the factorial of a number, I claim, is a recursive problem. All right, so 5 factorial then. What is 5 factorial? That's what, 5 times 4 times 3 times 2 times 1. We've seen that before, right? Does anybody see a smaller factorial inside of 5 factorial? Because that's what it needs to be recursive. Do you see a smaller factorial anywhere? Inside of 5 factorial? There are multiple answers. 1 factorial? Yeah, that's in there, right? What is 1 factorial? It's 1, so there's a 1 in there. That's correct. Can you find any bigger factorials in there, though? Good, yeah, you can find 4. And then everything in between, too, huh? Do we all see that? So, yeah, let me pick a different color. Just chilling right there is 4 factorial, secretly. Isn't that interesting? And then, of course, there's 3 factorial, sitting right there. 2 factorials right there. There's 1 factorial. They're all in there. And usually, what you want to do when you're breaking down a problem recursively is you want to find the next smallest one. So 5 factorial, you should go looking for 4. So 4 is the right one to find. It's like the biggest smaller one, if that makes sense. Okay? And that's going to be the secret. That's what we're going to use. All right? So once we notice that, now we can generalize this answer to be like not 5 factorial only, but like any factorial. Okay? Let's break it down. So we found the smaller factorial inside of 5 factorial. We noticed that 5 factorial equals, well, sure, it's this, but it's also, there's 4 factorial sitting right there. And so instead of all of this, we can say that 5 factorial equals 5 times 4 factorial, okay? And that's kind of interesting, okay? So that's a smaller problem. This generalizes, right? It works for different numbers too, like 7 factorial. What's that but 7 times 6 times 5 times 4 times 3 times 2 times 1? But all that, right, is 6 factorial. So 7 factorial is 7 times 6 factorial. just like 5 factorial is 5 times 4 factorial. Do you see the pattern? So we're going to use that in a second. So this is like we're solving 5 factorial in terms of itself, in terms of a smaller factorial problem. So right there, that's our smaller factorial finding problem. Which is interesting and cool. And this works for pretty much any number. You ask for 7 factorial, 6 factorial, 8 factorial, they all work like this. Like 7 factorial is 7 times 6 factorial, 5 factorial is 5 times 4 factorial. So in general, somebody asks for n factorial, that's equal to, well, your n times n minus 1 factorial. N times n minus 1 factorial. So you see how that generalizes both of these cases and every other one too, most of them at least. And we call that the recursive case. That's when you're solving the problem in terms of a smaller version of it. This is called the recursive case for the answer. And sadly, this is not good enough. We need one more case, all right? But that's most of it. That was our general case. How do you calculate n factorial? Well, n factorial is n times n minus 1 factorial. Like it works if n was 5, works if n is 7, works for most numbers. The last thing we need, though, is a way to stop this process, because it's always like handing off the problem to a smaller version, smaller and smaller and smaller. Eventually, we would like to stop, right? And then we can build up the answer from there. But because right now, like it would go on for infinity. We want to stop eventually, and that stopping condition is called a base case. And so, what you want to go looking for when you want to find a base case is, like, when do I have the answer at my fingertips? I don't have to do anything more. I don't have to do a smaller version of the problem. Like, it's already there. Okay? So, a good way to go hunting for this base case stopping condition is to just run this rule. Use that rule until it stops making sense. All right? So, let's try it. So, let's say we want to try to find 5 factorial. Well, running this rule with n equals 5, it's saying that, okay, 5 factorial is equal to 5 times 4 factorial. And that still checks out, right? That's correct. We notice that is right. Now, let's keep on running on 4 factorial. So, okay, what is 4 factorial according to this definition? Well, 4 factorial, you can break it down as 4 times 3 factorial. Just plug in 4 for n there, okay? That still makes sense, right? The world is still okay. Nothing's blown up yet. That is correct for 4 factorial. That is the right answer. So, you just keep working your way down until it stops making sense. So, okay, 3 factorial according to this is 3 times 2 factorial. And 2 factorial is equal to 2 times 1 factorial. That still makes sense, right? Okay, 1 factorial, according to this rule, is equal to 1 times 0 factorial. That starts looking weird, right? Technically, this is still fine. 0 factorial in math is defined to be 1, so this is technically still correct. Okay, can we go further? 0 factorial equals, well, according to this rule, 0 times negative 1 factorial. And this is where it starts making no sense at all, okay? So not only negative 1 factorial, factorials do not exist for negative numbers, first of all. So you can't go to there. You need to stop before then. And then also, the second you multiply by 0, like, it ruins everything we were trying to do, doesn't it? So this is when the world stops making sense. Everything blows up. You want to stop before you get here. So you could stop at 0 factorial, but I doubt most of us have seen that before. So let's just say that our stopping condition is, you ever ask for 1 factorial? If anybody ever comes to me and asks for 1 factorial, I don't need to run this rule. The answer for 1 factorial is just 1. Does that make sense? Like, that's your stopping point. You don't need to do any further work. And so, like, that can be your base case. Somebody comes asking for 1 factorial, you're done. The answer is 1. You don't have to do any further work down lower and lower. That's called the base case. That's how you find your stopping condition. You just keep on going until, like, things stop making sense. Or you're like, you know the answer, okay? And so that's the secret. Both of these taken together will find the factorial of a number, because you can just keep breaking it down. Like, all right, 5 times 4 times 3 times 2 times 1. And that is the answer, right? We're using both of our rules together. I hope that makes sense. Any questions about how we broke that down? Does that make a little bit of sense? Because we're going to turn this into code in a second, all right? That's going to be the name of this game. So yeah, the idea is, how do I want to do this? Let me just make a new slide, a blank slide, just to draw what's happening here. So again, with these rules, I just want to break it down so that you can kind of see where they're both coming from and why they're both going to work together and do the right thing. So with those in mind, let's say that somebody comes asking for 5 factorial. Well, we're going to run this rule, and we're going to go off and like, all right, it's equal to 5 times 4 factorial. And then what's 4 factorial? It's equal to 4 times 3 factorial. 3 is equal to 3 times 2 factorial, 2 times 1 factorial. And then this 1 factorial, we're going to define that to be 1. And that's like the base case. And so then we can start building the answer back up. Like, oh, the answer for 1 factorial is 1. We give it back to here. So now it's 2 times 1. So that means our answer for 2 factorial is 2. All right. And then 3 times the 2 for 2 factorial is 6. That's the answer for 3 factorial. And then 4 times the 6 that we got back from 3 factorial, that's the answer. That's 24, right? That's the answer for 4 factorial. That's correct. See how it's going to build its way back up after you've gotten to the base case. That's the secret. So then 5 times the 4 factorial, which is 24 now, we shove that up here, and we get, I think it's 120 as your final answer for 5 factorial. So that's both of the rules being used together. That's how it's going to work. Okay. So with that in mind, we can turn this into code. Okay. So let's see. Let me put this over here again. There it is. Let's write a function that computes the factorial recursively. All right, we can do that. A function can be recursive, and so it's going to look a little weird, though. Like, let's say that we've got this, like it's def fact, right? Fact of some n. We want to give back the factorial of n. That's what it's supposed to do. Computes the factorial or n factorial like that. So, okay, somebody asks us for n factorial. They're calling us like this. Like they're going to say like fact of 5. But this is a recursive problem, and so this is going to be a little weird. Inside of fact of n, we're going to call ourselves, because we're the smaller problem. We are the factorial solvers. We're going to call ourselves on a smaller version of the problem. It's going to look very odd. It's going to be like we're going to call fact of n minus 1 inside of the definition of fact of n, which is very odd. We've never seen that before. It's really weird, but really cool. It's going to work, all right? That's just because it's defined in terms of itself. Like, all right, somebody asks for n factorial, like we're the ones computing factorial. We have to call ourselves. That's the only way. Okay? Our hand is forced. So here's how you do it. To implement this from math into code, you just kind of like figure out like which case am I in? Am I in this case or this case? It'll be an if statement to start us off. Am I in the base case right now or am I in the recursive case? So I know that I'm in the base case if somebody wants fact of 1. So if n was 1 then. If somebody asked for fact of 1, that means n was 1 if n is equal to 1, double equals, remember. If n is equal to 1, that's my base case. And my final answer is just 1. Factorial of 1 is 1. I will return 1 to whoever asked for it. So that's perfect. Otherwise, else, that means it wasn't 1, n was not 1. So we're going to use the recursive case rule for that one. That means we're in the recursive case. And so what we have to do is our final answer, what we need to return is our n times the factorial of n minus 1. And the question is, how do we compute that? Well, we can throw it off to ourselves. That's going to be the secret. And it will work. You get to assume that it's going to work. All right? So we're going to call, we'll just call this x for a second. We need to call ourselves. We need to get the n minus 1 factorial. That's a call to fact of n minus 1. All right? Which seems very weird. It's like wishful thinking. Like, is this going to give us the right answer? Will this ever stop? The answer is yes, as long as we build up the answer correctly and we have our correct base case. So there I am making a smaller call to myself. And then I just get to like, all right, x will hold n minus 1 factorial. Just like I get to assume that's going to happen. And so if that really holds that, then my final answer is my n, right, times n minus 1 factorial, which I just shoved into x by calling myself, okay? N times x, which is wild, okay? So fact of 5, for example, if n is 5, it's going to go off and call fact of 4 and wait on that to get the answer back before it's done. Fact of 4, okay? Just like this. Like fact of 5 is going to wait and call fact of 4, which is going to call fact of 3 all the way down to the base case and work its way back up, okay? So let's code this up. That is the code. Are there any questions about the code itself before I show you it working? We might not be convinced that it's actually going to do anything right. It seems very circular. It might like infinite loop or something. But it really will work out. Watch. So let's go to idle, I guess. And then what lecture number is today? lecture 29. I guess I'll call this facts.py. And I said 29, right? Yeah, lecture 29. Facts.py, so you get to have it now. Let's see. Let's move this over here. Move this over here so we can get back to the slides themselves. There. All right. So here we go. Def fact of some n, and the job of this function is to compute n factorial. All right. Using recursion. Okay. So now, okay, we're either in the base case or the recursive case. Here, I can show that too, can't I? There we go. So if n is equal to 1, somebody asks for the fact of 1 then, if n was 1. So that's our base case. We return 1 back to whoever called us. We're done. Else, if that wasn't 1 then, we're in the recursive case. And so we need to go and figure out, like, we need to return n times n minus 1 factorial. And so, well, we are factorial. So we can ask ourselves, a smaller version of ourselves, for the fact of n minus 1, store it in a variable called x, and then we'll return n times that x. Okay? That'll be the secret. That's what I want to do there. And the factorial of 5 is 120, I think. And so let's print fact of 5. And like something that we know as well. Fact of, what's fact of 3? 3 times 2 times 1, that's just 6, right? So I should say 120 and 6 if this worked right. Let's try it. Crazy. Look at it. It's doing the right thing. It is getting the right answer. There are no loops in sight, even though this kind of seems like a looping thing, like a smaller number multiplying into a bigger number. None of that's happening. Magically, though, it's still computing the right answer. Isn't that weird? Are there any questions about this before I draw a picture of kind of how it's working? So we can, one thing we can do before I draw a picture is you can watch fact of 5 hand off the problem to fact of 4, and fact of 4 hand off the problem to fact of 3. I can print that out. Like every time somebody calls fact of n, I'll print this. Print, I am inside fact of whatever the n was, fact of n. This will print out like I'm inside of fact of 5, inside of fact of 4. So you're going to watch it work its way down to the base case for fact of 5 and for fact of 3. Whee. So here's the first call. Here's the call to fact of 5. You see how it's calling fact of 4, and then fact of 4 is going to like, all right, now I'm calling fact of 3, fact of 2, fact of 1. It's really going to make its way down to the final answer, to the base case, just like this drawing, and then start giving the answer back to whoever was asking for it. That's going to be the secret, all right? It's going to work its way back up, and eventually, all right, now I have the answer, I can give my answer back. So 120 eventually does that, and then fact of 3, again, just very similarly, it's going to start with fact of 3, then hand off the problem to a smaller version of itself, hand off the problem to a smaller version of itself, and fact of 1 is the base case. That's the smallest version, then it's done and it works its way back up, okay? So that's going to be how that kind of looks, and we can print that. And let me draw that now, all right? So to fully convince you why this is working and why it's doing the right thing, it's like looping without loops. I want to write or draw what's called a stack diagram for you, okay? So a stack diagram is like, think of it like a stack of papers. It's like a stack of work to be done, essentially. And that's going to be, I'm going to have a little piece of paper, essentially, for every function that's getting called. All right? So think of this, when I say stack, I mean like it's a stack of work to be done. Stack of work to be done. And it's also going to have like fact of 5 waiting on fact of 4, waiting on fact of 3. Like there's going to be a priority to it, and it's going to grow. Okay, so like it's also going to reference like the person below you wants your answer. So it's also going to talk about who wants whose answer. That'll make sense when I draw it. Who wants whose answer? Okay, so here's kind of how it's working. So at the very bottom level, that's like your outermost code. We kind of drew this once upon a time, right? You got your outermost code, and we are calling, let's say that I want to draw how the call to print fact of 5 will work. All right, so that's the first piece of like information. That's the first bit of work on my stack of work to be done. So I want to print fact of 5. Okay, and so that's the print function seeing that. It's like, all right, I need to print something. What do I need to print? I need to print whatever this is. And then it's like, I have no clue what fact of 5 is. I better call fact. Okay, so the next thing that happens, the next thing, like the stack of work to be done, grows. So print fact of 5. It's like, all right, I need to know fact of 5 so I can print that. So the print function is going to ask for, what is fact of 5 then? Give me a number. I can print numbers. I don't know this yet. I don't have the answer yet. Okay, so fact of 5 is the next thing to be done. Print is waiting on fact of 5. That's how you can kind of read that. Does that make sense? So you can see like print is waiting on fact of 5. Fact of 5 will give it its answer essentially when it's done. Like the person below you wants your answer. Okay, that's the secret. And I can also draw the variables involved as well. So like, all right, let's try to run fact of 5. So n was 5 in this case. You can think of it that way, like n right here is 5. And then what other variables does fact of 5 have? Well, we're not in the base case because 5 is not equal to 1. Well, we are in the recursive case. So this is going to try to make an x variable and put in it, right? Put in it the result of fact of 4. Does that make sense? It wants to put fact of 4 in this x variable, but that's supposed to be a number, right? We don't know the answer. We have to go and call fact of 4. So fact of 5 calls fact of 4. It's kind of gonna pause on this line because it needs the answer in order to continue. It doesn't have it yet. It has to go and it has to ask ever so nicely for fact of n minus 1 to do its job. All right, so fact of 5 is going to call fact of 4. And so that is more work to be done. Does that make sense? So fact of 4 is the star of the show right now. It's the one in charge. Its n is 4 now. It's another call to fact with a separate n value. Okay, and it's going to run all over again. So fact of 5 was waiting on this line, and then print was waiting on this line. Everybody below is waiting on the person above them. So print's waiting on fact of 5. Fact of 5 is waiting on fact of 4 right now. They're all paused. Okay, and fact of 4 is what's really running, the thing on the top of the stack. Okay. So, okay, we come in here with n being 4 now, still not 1, so we're going to hit the recursive case. We also need an x variable. So fact of 4 tries to make an x variable, and it's going to put in it, well, fact of 4 is defined in terms of, like, it's 4 times fact of 3, so it's going to try and call fact of 3. Does that make sense? It doesn't know the answer. It has to go and ask for it. It needs to get it back in order to continue. So fact of 4, just like fact of 5, is going to pause on this line for its own version of itself, and it still needs to fill in x. All right, so they're all waiting. X is blank for both of those. So now we got fact of 3. That's the thing that we're working on right now. Does that make sense, how it's handing off the problems? They're all paused. Fact of 5 and fact of 4, they're all waiting right here on the person above them. It's a new stack of work to be done. Okay, it's really cool the way that works. And so fact of 3, again, has its own n variable, which is 3 now. And it's going to try to make, well, it's still not 1. It's going to hit the recursive case again. It's going to try to make its own local x variable. And fact of 3 is defined in terms of fact of 2, so it has to go off and call fact of 2. It doesn't have that answer yet still. So it's going to wait on it. It's going to go and ask for it. All right, fact of 3 is going to go call fact of 2. And once it gets the answer back, right, it can multiply that by its 3, but it does not have that yet. Okay, it's not ready to return. They're all waiting. So everybody on the stack, like all these fact calls, they're waiting on this line. They're waiting on the person above them, the smaller factorial. They need that number back. They need that answer back in order to continue and like give their answer back to whoever called them. Okay, you see how it's all going to like stack on top of each other. Any questions about that? Because we're almost done. Right? We're getting our way to the base case. So this is a call to fact of 2. Again, it's got its own n, which is 2. Still not 1, so it's still the recursive case. It tries to make an x variable. And it's like, all right, fact of 2 equals 2 times fact of 1. So it has to go off and compute fact of 1. It will do that and try to shove that answer into an x variable. All right, so there it is. It's doing it. It's trying. And it's going to, again, pause in this line. It does not know what fact of 1 is. It has to go and ask fact, a smaller version of itself, for that answer and get a number back. Okay, so fact of 2 calls fact of 1. We're almost home free because that's our base case. Okay, so now fact of 2, 3, 4, and 5, all those guys, they're waiting on that line, aren't they, for the person above them, for the smaller factorial to complete. Okay, all of this code is running at once. They're all paused. The thing on top is the thing that's really running, but everybody else is waiting for the person above them to complete. All right. So fact_of_1 has its own, again, n variable. It's set to 1. That's just the parameter. And so, no, for some reason, sorry, you can't see that. There we go. Finally, right, n is 1 for this called effect. Yay. And so we're in the base case, and we return. When you say return inside of a function, it just immediately gives the answer back. It's done. And so fact_of_1 finally doesn't make any more variables, doesn't make an x or anything. It returns 1 back to whoever called it. And so it's always the person below you on the stack who called you. And so we're returning our answer back to them. So fact_of_1 returns 1 back to fact_of_2. And then we're home free because fact_of_1 now takes itself off the stack. Its job is done. It's not running anymore. Really, I should erase it, but just so you can look back at this later, I'm going to keep it there. So now fact_of_2 is on top of the stack. Really pretend that fact_of_1 has been erased. Fact_of_2 just got the answer back. It was waiting on this line so patiently for fact_of_1 to complete. It finally got an answer back. It got 1 back from fact_of_1. The answer was 1. It can place that in its x variable, 1. And it can do the rest of its job. So now it'll take that 1, multiply it by its n, which is 2, to compute fact_of_2 correctly, right? 2 times 1 is 2, and it will return that back to whoever called it, which was the person below it on the stack. So 1 times 2 is 2. It returns 2, and then its job is complete. Now fact_of_3 is the thing on top of the stack. It's the thing actually running. Do we see how this is starting to unwind? That's legitimately the technical term. The stack is unwinding right now, we say. All right. So fact_of_3, again, waiting even more patiently than fact_of_2 on that answer. It finally got an answer back for fact_of_2. The factorial of 2 is 2. It saw the number now. It's going to shove that into its x variable. It was waiting so patiently to do that. And now it can do its last line. So, all right, it's going to multiply its 3 times the factorial of 2, which it put in x, to make 6, and return that answer back to whoever called it as the correct factorial of 3. So it is correctly building up those smaller factorials and making it bigger factorials. So it's going to return 6 back to whoever called it, and that was fact_of_4. Does that make sense? Isn't that so cool? So it's looping without loops, just using this thing called the stack, a function calls. And so again, fact_of_4 was waiting on this line, oh man, and it finally saw an answer back for fact_of_3. It got its answer for fact_of_3 back, it saw 6, and it's going to shove that into its x variable. It's going to place 6 there. And then it can do the rest of its job. It can run its last line. It's going to multiply its n, 4, times the factorial of 3, which was 6. It got that back now. And return that answer back to whoever called it. So that's 24. And that is the correct factorial of 4. It is working. So that is 24. It's going to return that back. And then its job is done. So it's going to erase itself from the stack. And now it's fact_of_5, our final original call to factorial. It was waiting super patiently on this line for fact_of_4 to complete. It had a lot of work to do, right? Had smaller things to call. We're finally back in fact_of_5. It waited on fact_of_4 for the factorial of 4 answer. It got it back. It sees 24, and it's ready to place that in its x variable. So it's going to do 24, put it right there. And then finally, it can run its last line. So it needs to return an answer of its 5 times the factorial of 4, which it placed in the x variable, and that's 120. And it's going to return that back to whoever called it, 120. 120. Now it's done. Wow, now we're back in print. Print was like, what was fact_of_5? I need to print something. I can't print fact_of_5 unless I have its answer. It has the answer now of 120, and so here's like the screen. Now it's going to print 120, and then print's job is done. Does that make sense? That's how it's going to like make its way down to the base case, and then start building up the answer from there. It's like, all right, multiply by 2, multiply that answer by 3, by 4, by 5. It really eventually does it right. It's going to build those smaller factorials correctly and use them to correctly build the bigger factorials. And so that is the magic of the fact function, of recursion and factorial. Like, it's not immediately obvious that you calling yourself is going to make any progress at all or actually work. But really, in reality, because of what we've seen, you can just assume, like, all right, somebody asked for fact_of_5, like, this is really going to compute fact_of_4 correctly. You can just assume that. You don't have to have any extra thought. Like, it's going to make its way down there and do it right. As long as you build up the answer correctly and have the correct base case, it really will work. Okay. So that's the moral of the story. It is definitely a harder concept. I spend potentially over a week on it in my CSCI 40 class. So recursion is not the easiest thing in the world. So if you understood any of that today, I'm proud of you. And it is it will all get better from here. Okay, so I think that's what I wanted to say today. That is recursion in a nutshell. We're finding problems inside of themselves. Any questions about that? All right, because I think that's where I want to stop for the day. No new assignments, so I'll post all these slides and stuff. And next week is the last week of classes, and so all we're going to do is have a final review for the final. Okay, so just both of those days we'll do like Python and stuff, and then also some non-programming stuff. But I'll talk about everything else there. But yeah, no new topics. This was the last new stuff today. Okay, and so that's I think all that I want to record.